Hello, everyone. Welcome to the afternoon session. I hope everyone enjoyed their lunch. I'll take that as a yes. Um, so just a couple of brief things. As always, please set your phones to silent. Bear in mind, if you do need the toilet, they're in the room to the left. However, please try and avoid going during the course of the presentation because it can be quite distracting, both for the presenters and the audience. I think that's everything. So, kicking off the afternoon session, we have Emma Duckworth and Giorgio Mihaylov. I hope I pronounced your name correctly. Fantastic. Okay. All those courses in Eastern European languages paid off. They're talking about AI and complex industrial systems. So Emma's Director of Data Science at GSK Consumer Healthcare, focused on the strategic use of data science and AI to serve customers and deliver everyday health with humanity. Her team is responsible for researching and building AI solutions across supply chain, R&D and marketing. She started her career in data science at IBM and since has built and led data science teams at several consumer-focused startups. Giorgi is a principal data scientist at GSK Consumer Healthcare. He's developed original and impactful applications of data science, advanced mathematical modeling, ML and AI in different industrial contexts. The main focus of his current work is modeling and AI-driven optimization of complex industrial systems. Can we have a round of applause for our presenters, please? Thank you.
Awesome. Well, thank you so much. I don't really need to give an intro after that. But we just wanted to say a huge thank you to everyone for having us. It is so exciting to be back at an in-person event. This is the first time I actually get to see Gueorgui with his laser pointer, which is going to be, it's been very hyped and we're very excited for it. But a huge thank you to Data Science Festival and Data Idols for this awesome event. And thank you all for coming. This is great to see everyone here. So we come from GSK Consumer Healthcare. For those of you who don't know, we are on track to being the world's largest consumer healthcare company. That means that we have hundreds of brands that are used by consumers all over the world, really with the focus of delivering everyday health with humanity. This means that we make our products, so we make products in over 30 plants around the world, and we deliver those products to over 100 countries, thousands of retailers, and we need to make sure we do this to the highest quality. So we often get asked the question, and we have to ask this ourselves, of where can we have the greatest impact with AI and data science? How can we deliver the greatest value, both to the company, but also to our consumers? And how can we do this in a way that's really strategic and thinking for the long term? And we also, we follow agile principles, and we like to often hear, and we often hear this in software development and things like this of, start small and iterate. But when you're talking a global supply chain, where maybe your smallest unit of measurement is, say, a shipping container, what does start small mean? And actually, what is an acceptable level of risk? And how can you be responsible when you're applying AI in a very, very tangible and real-world setting? And this is something that we're going to hopefully go through and answer today. And this is really important, not just for supply chain issues, but for some of the biggest issues that are impacting all of us, and specifically that we really care about as a company. We have really ambitious climate goals. At GSK, we really believe that you can't have healthy people without a healthy planet. And we think that data science and AI is one of the critical ingredients for us solving and meeting some of these challenges. So I'm going to hand over to Gueorgui, who's going to tell us how complex systems and modeling whole complex systems are the solution. Gueorgui.
Thank you very much. So, AI is highly impactful in many industrial applications, and in recent years we saw enormous progress in computer vision applications, in forecasting applications, in smart manufacturing applications. But one of the main characteristics of AI is that it can manage high number of degrees of freedom and sets of highly non-trivial constraints. So actually, we can build prescriptive solutions able to optimize, optimally orchestrate, or keep under optimal control or design our interventions into very complicated systems. So I mentioned complicated systems, but actually the title of the talk is complex systems. So what is a complex system? A complex system, and I have to give credit to Wikipedia on this, is a system composed by many components which may interact with each other. So this a bit like sounds a bit like, discovering the hot water, but actually the actual defining property of a complex system is the emergent behavior. Emergent behavior a system manifests global, when a system manifests global properties, that its parts or agents in the system do not manifest on their own. So this is, in a way, the defining property of a complex system. The fact that a complex system displays non-trivial, global, collective, or emergent behavior. And people do a lot of research in this direction. For example, a few years ago, I attended Applied Mathematics conference, and there was a professor from MIT, her name was Nancy Leveson, who actually did a very interesting analysis of the crash of the Schiaparelli mass landing module. And apparently, according to that analysis, all the subsystems worked perfectly. So it was the communication, it was how the system worked in its totality that made the landing module crash. So it was the miscommunication between the parachute and so on and so forth. I invite you to go and read that because it's really interesting. But this is the moment when people started realizing, and people started doing a lot of research in this direction. And actually important properties of complex systems, of complex engineering and complex industrial systems turn out to be global, turn out to be collective or emergent, such as reliability, as in the case of the Schiaparelli module, or safety, but as well efficiency and resilience, very importantly, resilience. So on page number 1 of many publications on complex system, you can find this example. And this is the big blackout that happened in the northeast of the United States in 2003. And it's actually a very good example of emergent behavior in action. So if you read what happened in that case, you can see that there were a cascade of very small and very confined events around the system, like, of small and confined events in the power grid. Like, for example, at certain point, there is an interruption of one of the high voltage connections. Or, according to the report, at certain points, some employee went for lunch and forgot to turn on some monitoring tool, and so on and so forth. But these small and really isolated events created a cascade or a really non-local response of the system with this propagation of massive shock waves around the system. You can see that they went even down to Florida, and at certain points actually provoked this, the blackout situation. So actually, you can see that small events and isolated events provoked a collective, really non-trivial collective behavior of that system, which led to the propagation of the shock wave, and basically that shock wave started knocking out the generation plants one after one, and that's what happened in the end. So collective behavior can be is extremely important in complex industrial systems. And complex industrial systems, as in this case happened, are able to amplify those signals. So they manifest, exhibit non-linear behavior, like, for example, in this case. So non-linear behavior means that very small interventions on very small deviations of the system from some sort of operational regime, standard operational regime, can lead to really big explosive deviations and large-scale effects. So in this specific case, what happened is that I think one of the blades of the turbofan was put slightly offset, and that provoked what you see on the picture. So such systems are extremely difficult to control. Such systems are extremely difficult to predict. You know, what's going to happen? What is going to be their behavior? What is going to be their behavior in a situation like that? And therefore, for example, you still are mandated by law to make destructive tests in systems like that, to see how they react in those circumstances. And is there any chance to save the aircraft, for example, right? So, and by the way, these things are really full of sensors. So it's not that we don't have visibility on what's going on inside them. It's that modeling what's going on inside them, it's really complicated. So global behavior, non-trivial global behavior, and really non-linearity. So there's a successful theoretical paradigm that kind of explains when emergent behavior occurs. And it says that complexity arises when agents or subsystem in a system manifest contradicting local behavior. So what you see on the picture here is one of the most popular physical models, spin glass. This is called the spin glass, which actually is based on the fact that you have very simple one-to-one interaction between these things, and these things are magnetic dipoles, which can behave ferromagnetically or antiferromagnetic, which basically means that if you have two of them, you can very easily say what is the best configuration for their energy. It's like that. You know, but you have many of them. If you have a three-dimensional or multi-dimensional lattice of those, it becomes extremely difficult to understand what, or to model what is the global behavior of this system. And you see these global large-scale oscillations and other non-trivial phenomena, such as phase transitions or shockwave propagations or other things like that. So it's not the behavior of a single agent, because if you pick two single agents, it's very similar. It's very, very simple understanding their interaction. It's the global, the collective behavior again. So industrial systems can be very complex. And the reason for that, in view of the theoretical paradigm that I just explained, is that very often you have different or even multiple levels of overlaying interaction or overlaying layers, and these overlaying layers actually have contradicting dynamics. So an example in supply chain, if you have complex supply chain or multi-echelon supply chain in which, as you see here, for example, you have your retailer, but then you have logistics, you have the wholesaler, you have other piece of logistics or other leg of logistics, and then you have some sort of manufacturing here and so on and so forth. Before manufacturing, you need to purchase your raw materials and so on and so forth. So you have multiple levels. What happens is that very often the KPIs or the dynamics or what is good at one level might not be optimal for the level after, might not be great, you know? And there are tons of examples like that. For example, if you are a batch manufacturer, if you manufacture your stuff in batches, if you're the manufacturer, then you'd like to have very big batches because this reduces the frequency on the machines, because it's easy to manage and so on and so forth. But that's not great for example, if you need to trace your batches, or because they can end up everywhere, right, if they are too big, or inventory management, or inventory holding, or logistics. So having two big batches is not great for everyone else in your company, hypothetically, if you're the manufacturer. Again, container utilization is a great KPI for logistics, right? You don't want to ship air around the world. You would like to, ship stuff for which you pay. However, so there is a simple solution to that. You just keep a lot of inventory everywhere, and you make sure that you can wait and fill your containers. But on the other hand, that's not great for everyone else, because keeping huge inventories around the world means blocking working capital, right? So what is good in that case? Who knows? Right? So it's a non-trivial question. And you have multiple, if you have many of these levels, what happens? It happens that in your planning cycle, so typically what happens in a multi-echelon supply chain or a complex supply chain is that goods flow like that, but very often the information flows the other way around. So especially, for example, if you have this forecasting signal on what is going to be the demand, you get it from the retailer, who is actually the closest to the actual consumers. And then the retailer makes their planning cycle and then communicate also to the previous level of what's going to be the workload or the amount of stock they're expecting. But then the next level does their own planning cycle and so on and so forth. And remember that the KPIs, what is good for them, might be very different from what is good for the neighboring segments. And what happens here? This is a very well-known effect in multi-echelon supply chains called the bullwhip effect. That basically you start with a signal like that, and then going back, your forecast, your workload forecast, your volume forecast increases enormously. So what happens? It happens that multi-echelon complex supply chains amplify signals. They amplify signals exactly as we saw before. And this is not just an error propagation thing. It's not just that, you want to be over-insured with respect to the forecast of your neighbors. It's that your KPIs are conflicting with the ones of your neighbor. And again, very often you can think easily of examples where a major disruption of the harbor, a major disruption of customs, or any kind of phenomenon like the Suez Channel, can paralyze or can have enormous implications on global supply chains, having a cascade of events where basically the service is disrupted for in quite an unpredicted way, very often. Okay, so we live in a very, very interesting historical moment. So now, actually, we have commercially we have commercially available data infrastructure which provides exceptional and unprecedented visibility, digital visibility, on a lot of these processes. We have commercially available computational power that is able to run very, very complex algorithmic tasks. And it's commercially available. You don't need a Pentagon computer, basically, if you want to run any of these algorithms. So right now, in this moment, there are enormous opportunities for advanced modeling, advanced mathematical modeling, advanced algorithmic modeling of complex industrial and engineering systems. In a way, mathematics and the development of the theory is catching up with the opportunities that the visibility and the computational resources are allowing. And there are a few titles that you can see as, as an illustration to that fact. For example, mathematical big data needs big theory too. So this is one of these examples. So important leading research institutions are very aware of that. For example, one of the big research programs of the Alan Turing Institute, the British national champion in AI, is actually focused on development and understanding and modeling of complex engineering systems. And so on and so forth. This is very well captured, for example, in the AI roadmap of the UK AI Council. By the way, some of you might have heard that the Italian physicist Giorgio Parisi wins the 2021 Nobel Prize in Physics for his research in complex systems. Parisi has developed a paradigm that goes beyond condensed matter. His theories can be applied at all scales: glass, the brain, finance, the flight of birds, lasers, and much more. And I would add to this list something which is relatively recent. Actually, some optimization algorithms in deep learning are very strongly inspired by his work in spin glasses, on spin glasses. He worked quite a lot on spin glasses, and it was vitrification and phase transitions. So some of you might be, very enthused by these facts. Some of you might not. But, mathematics has this dual nature. It is both an independent discipline valued for precision and intrinsic beauty, but it also provides an extremely rich set of tools for the world of applications. And there are many institutions and many reports in recent years which have highlighted very strongly this fact that mathematical modeling of complex systems provides the highest return of investment across basically all the scientific disciplines. And it's in these ranges here. So, very importantly, a strategic view on industrial applications of AI must consider these strong scientific and industrial trends. You cannot ignore them because they are extremely impactful. So, materialize the opportunities of large-scale modeling and orchestration of complex systems. You should try, or in these cases, there is opportunity. You should try to materialize the opportunities of large-scale modeling and orchestration of complex industrial systems to maximize competitive advantage for companies like ours. Okay, so how? It's a really, really non-trivial question. So, as I explained, a strategic view requires you to consider the complexity of the system. Agile delivery is a great tactical tool, but you need to be at a certain point to face the actual complexity and actually the global scale of your phenomenon, the collective scale of your phenomenon. Am I right?
Yeah.
So, one of the questions that Emma asked at the very beginning was, what does it mean starting small? And this is a non-trivial question. This is a really difficult question in this case, because if I refer you back to the jet engine, what does it mean starting small if you model a system like that? You first explore a very tiny engine, or you have the full-size engine and explode it just a tiny bit? So what is starting small? And the answer is that basically the optimization, the orchestration, and the modeling of complex industrial systems is very bespoke and very business specific. Because this is the moment, this is the level where all the complexities of your own sector, all the complexities of your own industrial reality have really important impact. And they all come together. But again, we all know the let's say the tactical ambition or the delivery ambition of starting small, learning fast, and then deliver value. But actually, we're doing a lot of original research and a lot of original thinking and a lot of review of what other companies and what is the state-of-the-art thinking in this area to propose the answer to the how question in the what happened? Yeah, in the GSK reality. So, here I just list a few elements of potentially successful or potentially useful modeling approach or a theory which is able to help in some cases tackling the description and modeling of complexity. For example, you need to have the system formalism. So you need to implement the formalism in terms of agents, subsystems, and interactions between them, because this is the way that you capture many of these phenomena. Furthermore, you need to include stochasticity or some level of chaos. You need to allow stochasticity to be introduced to your system, and the way how you do it might be very difficult and very different in different cases. So this thing here, collective or functional degrees of freedom, this is actually an interesting point, and leads back to, if you wish, functional analysis. There are situations where you can describe the state of like an agent in a system with some local description in terms of parameters, or the description can live in some parameter space. But then actually what captures the dynamics, what describes the dynamics, is some set of functional degrees of freedom, which actually are collective. They're global. They, as functions on manifolds, for example, or as functions on sets, they capture the dynamics globally, not just the dynamics of an isolated agent. Or, this is, becomes a bit more specific, but geometry-dependent interactions, or you can represent the interactions between different agents as a collective phenomenon, as a field that propagates on a hypothetical manifold or something like that. And what really proved to be extremely impactful, was the importance of topology of the configuration space. So you can have different configurations, and if these different configurations can have non-trivial topological structure, non-trivial topological structure. And this topological structure proved to be extremely impactful in a lot of applications, such as brain, studies of the brain, studies of complex logistics network, studies of delivery networks, and so on and so forth. The multiple interactions between agents. Okay. So, if you would like to learn more, there was an interesting, lecture here, in which the attempt or the idea was to combine all these elements in just one consistent theory. So I kind of recommend this on the event of the London Mathematical Society and the Institute of Mathematics and its Applications. Joint meeting on precisely that, topological methods in data science. So, in the following few minutes, I would like to show you a few examples without going into too much detail, with the idea that some of these comments or some of these concepts or some of the things that we describe here start to materialize. Like, for example, this one. So, we were asked some years ago to describe the productive efficiency of food processing, packaging factories. And we were asked to find some sort of the answer of a classical business intelligence problem, which was infer the commercial behavior of a plant by monitoring the technical engineering performance of the packaging lines. So the only way in which we succeed in answering both these questions was treating a plant as a complex system combined by agents, composed by agents in it, and those agents were actually the packaging lines. And we had some sort of the description of every single packaging line, because the KPIs we were capturing, performance indicators for every single plant, were actually measured at a machine level. But what really solved the problem was this manifold learning approach based on collective functional degrees of freedom. So basically we did some sort of spectral analysis in which the behavior of many of these agents in the same moment were captured by functions. So not the individual description of every single agent, but some sort of embedding them in a feature space which is collective, of collective degrees of freedom. And here are the papers. for further reading, if you'd like, you can check this paper. So in the specific, in this case, for answering the second question, obviously we tried all the standard artillery of deep learning and machine learning methods, and it was like very interesting how nothing worked. But a simple geometric idea, which was based on this collective behavior or collective capturing all of the plants going to, all of the system agents in the plants doing something together, was a thing that worked, quite interestingly. So here's just an example of this. So here are our classes of plants. You can see in this space of these global functional features, basically, you can interpret this as, so we interpreted this as segments with different levels of productive efficiency. And these are measurements taken on every single plant, but actually these are with respect to these global collective degrees of freedom. And here is what happens in the real space, in the physical space of this. So it's like you cannot understand anything here, right? But what happens really nicely is that over the years, for example, you can see how a plant, so these are measurements on the machines in one plant, was very stably and very reliably staying in a high performance segment, and then gradually it migrated to a low performance segment. Remember the flight of the birds? So basically, you see, this is a collective behavior, this is a collective motion which was really nicely captured by this model. Again, non-local, but global, collective. Another example, which is a piece of work which is in progress. It's collaboration with UCL as part of our data science or data for good program. We're developing this piece of research together with UCL, and it's basically, we're trying to model the diagnostic and treatment pathways of several diseases. So it's apparently a completely different example, as you can see. So the pathways are certain treatments and certain diagnoses, if you wish, interventions, which happen over time, and then be quite complicated and ramified over time. So we are trying to model these pathways and especially understand the impact of COVID, because COVID, for example, caused the delays or capacity reductions or problems at many different levels of those pathways. So together with UCL, we are trying to apply similar techniques, so advanced supply chain optimization techniques or management methods, in order to analyze and model the optimal pathways, understand where are the problems, understand where are the bottlenecks. And also in this case, obviously, the main idea is maximize the benefits for the patients by increasing or modeling the reliability of those systems and maximizing the benefit, in terms of speed and efficiency for them. Very interestingly, and I'm not going in detail on these examples, but very interesting, you can see how this system of, if you treat this system, this system of pathways as a ramification of different possible events, or in a way a supply chain problem, it's very important to see how it reacts globally, it reacts as a system to certain events, and there is kind of, we don't find an alternative way of describe those phenomena unless you describe them as just one system. Very quickly, I would like to mention this example here, which is our internal example in GSK. So the AI inventory planner, we solved the classic problem with a lot of help from Lancaster University. We solved the classical problem, and we want to guarantee service levels whilst optimizing inventory. The original element in which we included here was a very good digital visibility, which we had on international logistics supply operations. So that information was leveraged was very strongly integrated in the inventory management model. An interesting aspect of this example is not the complexity of the system. It was moderately complex, let's say, but with the fact that we were able to build very, very reliable and very interesting digital twin simulations, which were able to test, show, and literally show the performance of this tool compared to other possible solutions, specifically in the GSK reality. So we implemented a lot of the important operational constraints, and we compared the performance of that tool even before starting to think about implementing it, to what is the situation right now, to what is the situation with the current technical suite of available systems. And here I just want to show this example very quickly. So this is a video. You'll see week by week how inventories are evolving over here. Here you'll see if the tool recommends a normal order or an emergency order. These are different inventories because there are different ways and you can measure inventory in transit and so on and so forth. Here you'll see the supply pipeline. So we are forecasting how our shipments are traveling towards us. Here you see the the orders that the tool is suggesting and the demand forecast. And here it's a very important element, which is the trigger that tells you if we need or not need to, by any chance, place an emergency order, right? So if there is a strong danger of stock out, and there is quite an interesting probabilistic computation that underpins this model. At a certain point, you'll see that the screen changes, and it's precisely the comparison, the digital twin comparison that I mentioned before. The comparison between the performance of a tool like that. Oh, come on. Why is it not working? Okay, I'll play. So this is how the tool makes decisions at every review period, actually suggests the decisions. Here are the small emergency orders that happen if there is a probability of stock out. And as you can see here, there's the comparison of week by week on this specific time frame of what is the suggested behavior, the behavior suggested by the tool. And this is what happened with the currently available systems in here. And as you can see, so I'm not going to play this back, but as you can see, the requested service levels were reached with more efficient inventory, with more efficient inventory policy. But again, I wanted to share this example mostly mostly for the digital twin aspect of it, because actually it's interesting when you're able to have sophisticated digital twins powered by sophisticated mathematical models and then show you the behavior or the performance of solutions like that in reality. Okay, so this is a big project, and it's actually our way, or one of the ways we're working on answering the how question, how we will be able to understand complexity and to take advantage, if you wish, or to materialize the opportunities in complexity modeling that the current historical moment offers, and is a project called AI-powered end-to-end optimization engine for the GSK Consumer Healthcare global supply chain. And it's a collaboration with leading research institutions, such as Imperial College London, King's College London, Lancaster University, and also our industrial partners from DataSpan. GSK business goals, in a way, translate in a multi-objective optimization problem, because we would like to deliver top quality of our products to, excellent service to all customers. But in the meantime, we want to be maximally efficient. We would like to maximize the sustainability of our supply chain. We also would like to make our supply chain resilient. And resilience becomes more and more important. And I'm sure you've heard about disruptions and problems with supply chain, different supply chains in the last months. So it becomes an interesting and really non-trivial multi-objective optimization problem. And the OTC sector, the over-the-counter sector, has its own complexity because, it needs to be the maximum possible quality and the maximum possible compliance with a number of rules and a number of regulations, which are, by the way, different and complicated in different countries, and at the same time, being efficient as a business organization. So, in that, we are working with all these leading research institutions, and we are really applying and thinking in terms of state-of-the-art research, in operations research, optimization techniques, supply chain management, mathematical modeling. And core component of this is going to be actually really good understanding and being able to model and being able to take advantage from the understanding of this complexity. So one of the key scientific ideas that we would like to implement is actually implement the end-to-end view on what's going on as a structural element of that theory, as a structural element of that project. So privileging less the, let's say, single component or modular solution. And we believe that, you know, as I said, this is our one of our big projects that aims at answering the how question. And I will hand back over to Emma.
Thank you so much. So what are our conclusions from this? Hopefully you will have been convinced by now that now is the time to get into this kind of modeling. We are at this inflection point. We can actually start modeling these complex systems. And actually, this is a place where if you want to deliver real value and also be responsible thinking about the risks that can start to come with doing proper data science work in action and AI in action, you need to start modeling the whole system. You know, if you need to try and convince different people that this is where we should be working, it's beautiful, it's Nobel Prize winning, and it's going to deliver the greatest return. This is really, you know, where when we're thinking strategically about where to put investments, this is it. We think it's going to be critical for solving some of the biggest issues facing all of us, whether that's sustainability, whether it's coming up to big solutions to things like COVID, etc. This is where the future is, and this is actually where the UK is putting so much of its energy into research and a chance for us to be real global leaders in the field. It's really, really exciting, and we're excited to be part of it. And if you want to come and hear more and talk to us, we're around later, so please do reach out. And thank you. Thank you, Giorgio.
Thank you.
Thank you, Giorgio and Emma. We only have a very short amount of time for questions. So does anyone have any questions on anything? Yes, the gentleman at the front.
So you mentioned using different manifolds to model different problems. Have you been making use of hyperbolic geometry?
You want me to repeat the question?
Yes,
Yes, thank you. So the question was, amongst different manifold learning methods that we've been using in the past for dealing with some of these complex problems, was there a case where we used hyperbolic geometry? I haven't used that personally, but I'm aware of the methods that actually hyperbolic geometry and, you know, redefining distances on hyperbolic manifolds can be very useful. So no, actually yes. In one logistics example, where we had to balance in certain way the weight on different delivery routes, there was an occasion which we actually used something very similar, kind of hyperbolic manifold in which you put, you know, the distance on the delivery points which are further from, let's say, your delivery hub counts more with respect to. So yes, I'm aware of this kind of manifold learning approach, and I've used something quite similar in for example, in a very practical logistics application.
Thank you, Giorgio and Emma. A round of applause, please, ladies and gentlemen.
Thank you.